Maybe I will give you a short history that actually already mentioned by Mr. Saiful, and also dark matter theory, the concept of dark matter theory, and then we go to the rotation curve of the spiral galaxies, and also the case study of Orion dwarf galaxy, and last but not least the conclusions. Okay. As Mr. Saiful said before, actually dark matter is the solution of the cosmological problems, especially on galaxies rotation. Okay, so but who are the one who made these discoveries? Okay, first is from Stromberg. Okay, they actually give some clues that actually Milky Way is rotating, and then Lindblad give a strong evidence of the Milky Way actually rotating, and lastly Wood shows that our galaxy is rotating in differential rotations, means that every point in a galaxy will rotate with respect to different angular velocity. Okay, and then from there, in 1932, Wood showed that actually dark matter exists in galaxy disk using the Jeans equation. Okay, and in 1933, Zwicky, that already mentioned by Mr. Saiful, the dark matter exists in coma cluster by using the virial theorem. Okay, and Vera Rubin and also Ken Ford, they show that the dark matter exists in spiral galaxies. Okay, especially spiral galaxies in type A to type C. Okay, and they use rotation curve for to show that the dark matter exists in spiral galaxies. Okay, so my presentation is more on rotation curve. Okay, now dark matter theory is a better general description of the universe that we see. Okay, and actually, as already mentioned by Mr. Saiful, the relation we will look on relation between luminous mass and versus gravitational mass. Okay. The problem is that when we calculate the luminous mass and also the gravitational mass, it is not equal. Okay, the gravitational mass is more than the luminous mass. So why is that so? Okay, so that's why the physicists, the astrophysicists suggest that there is another component that exists in our universe, that it is dark matter. Okay, so discrepancies of measurement between luminous mass and gravitational mass suggest the existence of dark matter. Okay, from this equation also, okay, Mr it refers to the gravitating mass. Okay, and the MLR it refers to the luminous mass of the baryonic components. Okay, so since that this term is greater than this term, okay, so that's why we have to add more. We have to add another component. This is the dark matter component, the MHR. Okay, it refers to the dark matter halo. But how we are going to find this? Okay, first, okay, we consider the luminous mass. Okay, as we all know that we have several types of galaxies, that it is spiral, ellipticals, okay, dwarf. But all of these galaxies only just have one type of dark halo. But for their luminous components, we have to consider a few components in spiral. For example, it depends on the morphological of the galaxies. Okay, for example, for the spirals, we have the stellar disk, bulge, and also the H1 disk. So in order to get the luminous mass, we need to consider all these components, all the matter that consists in this, all these three components. And then for the criticals and also the dwarf spheroidal, we have to consider the stellar spheroid. For the gravitating mass, okay, this is the Newton's law. So so in the end, we have the mass equal to RV squared over G. So therefore, we can conclude that mass is actually proportional to RV squared and proportional to the dispersion velocity. Okay, so V squared is the rotational velocity observation that we can plot it, and we can have the rotation curve. So from there we can calculate the mass in terms of radius from the rotational velocity observation. Okay, but how we are going to get this rotation curve? Okay, so this is the disk characteristic that we need to consider. First is the sky coordinates of the galaxy, and then systemic velocity, circular velocity, and also the inclination angle, and then we can plug in all the values, and then we will have the rotational velocity. Then we can plot the rotation curve. Okay, so this is the rotation curve of a spiral galaxies. Okay, as I mentioned before, there is a discrepancy between the gravitating mass and also the luminous mass. Okay, from this plot actually, there is a discrepancy between the observed and also from the theory. Okay, the red curve is from the observation that we observe. The blue curve is from our prediction, the theory. Okay, we can say, for example, when we have a short string and we need to rotate, and if we compare with the long string and we try to rotate, of course the shorter string will move faster, will rotate more faster rather than the long string. Okay, but why we can't? Why the predictions doesn't fit with the observation? So that's why we say that there is actually more matter in this in galaxies. Okay, for the spiral disk, we have to consider first the stellar disk. Okay, spiral galaxies are galaxies with a rotating disk of star and gas. Okay, because star and gas we consider as the luminous matter. Okay, so this is the formula from the Freeman. Ken Freeman is the one of the astronomer, one of the active researcher in dark matter. Okay, so he proposed this. Okay, in order to get the star distribution. Okay, so from this equation, RD is the disk scaling, disk length scale. Okay, and we get this value is actually from the optical radius RD, that it is R optical equal to 3.2 RD, and then this is the I naught, the central value, and MD is the disk mass. Okay, and then we need to consider the gas surface density. Okay, why we need to consider the H1 data that we can get it from the radio telescope. Okay, because actually the radius that we can cover is outer. We say that it is outer radii, right? More than the optical radius. So that's why we consider the H1 gas. Okay, extended to 8 to 40 RD. Okay, and then from this curve, from this graph also, shows the flattish radial distribution. Okay, but for the H2 we omit the H2 because if you look at this curve, it's only stop at here, at this point. Okay? So that's why we consider, so it can be omit and we consider the H1 data. From there, we can start with our rotation curve analysis. Okay, so rotation curve analysis gives astronomers a way to characterize the amount of dark matter in galaxy. Okay, consider the following model. This is our model. Okay, that we need to fit with the observation data. Okay, where V squared disk equal to this. Okay, from I-band photometry, and this is the Bessel function, and then this is V squared H1. It is from H1 observations, and then this is V squared halo. It is equal to this. Okay, but actually there are a different choice of dark matter halo density. There is Burkert, isothermal, NFW, and also the INES2. But all this profile actually we can choose according to the galaxies. If we study for the spiral galaxy, it will be different density profile that we are going to use. If we are going to study the dwarf galaxy, we will use different density profile. Okay, but for my study, I use the Burkert density profile because my study is more to dwarf galaxy. Okay, so these are the halo model. This is the Burkert, the isothermal, and also the this is the NFW. Okay, and then from when we do the fitting, and we will have these three parameters, that it is disk mass, that it is MD, and then the halo central density, the rho naught, and the halo core radius, R naught. Okay, so we will have these three parameters from the best fitting method. Okay, so this is the result, the modeling result. Okay, we can categorize it from the lowest luminosities to the highest luminosities. Actually, we want to make a conclusion for the lowest luminosity galaxies and also the highest luminosity. What is the distribution of the dark matter for from lowest to the highest luminosities galaxies? Okay. Okay. If we look at these galaxies for the lowest luminosities, okay, to get the best fitting, the halo component is more than the disk component. Okay, so means that for the lowest luminosities galaxies will give more dark matter distribution rather than the highest luminosity galaxies. Okay. Okay, and this is when we consider four factors. It shows the four-dimensional graph. This is for the fraction of dark matter. This is the halo central density, and this is the core radius, and this one it refers to the luminosity. Okay. As the luminosity decreasing, then you can get the core radius also become smaller, and also for the halo central density and also the direction of the matter. Okay, or you can just look at this statement. Actually, all structured dark matter and luminous matter parameters are related with luminosity. Smaller galaxies are denser and have a higher proportion of dark matter. Okay, and this is from my study for Orion Dwarf Galaxy. I get the data from the co-worker of my supervisor, John Cannon, and actually our aim is to get the dark matter distribution on Orion Dwarf Galaxy using rotation curve, because rotation curve is for the single galaxy. Okay, and why we choose Orion Dwarf? Actually, because many dwarfs show solid body rotation. Okay, and Orion Dwarf also it is H1 gas rich. Okay, so the rotation the data is from the VLA H1 spectral line and also from the optical telescope. Okay, and the H1 optical observation of the Orion Dwarf Galaxy originally discovered by Giovanelli. Subsequent Archival observation show it to be H1 rich. So actually, that is also why we choose the Orion Dwarf Galaxy, because it is H1 rich. Okay, and actually this is just the rotation curve plot, and this is the observation data that we get. Okay, so this is the data observation. So we need to, we will model the rotation curve and fit with this observation data. Okay, so we will consider the B squared halo. They already show the formula for the B squared halo. But for this, I choose for the Burkert density that I mentioned before, and the H1 data. Okay, this is the H1 data, and then it is from the optical radio telescope. Okay, and then B squared disk. Okay, the formula that I already showed previously. Okay, and then this is my result. Okay, so this is the best fit curve that I get. Okay, and then this is the halo, and this is the disk distribution. Okay, but of course there is a lot of work need to be done after this. Okay, in terms of maybe I have to because actually there is the value of chi-square there, but I think I forgot to put it. Okay, here. Okay, this is the value of three parameters that we get from the best fitting: the disk mass, core density, and also the core radius. And the value of chi-square is 4.46. But maybe I will improve this in terms of minimize the value of chi-square to get more get the curve more fit to the observation data. So there is a lot of things, and also I'm waiting for the other data observation from my supervisor to do more rotation curve analysis, so then we can you can apply to the other it is more on universal rotation curve. Okay. Yeah, I think that's all. So I want to thank to Radio Cosmology Research Laboratory and also the mathematics section, and Agensi Angkasa, and also my supervisor.